So signal flow graphs. So signal flow graphs are actually quite a nice way of representing processing in systems in a way which is a bit reminiscent of circuit diagrams. And of course, if you use things like Simulink, it also fits very nicely into that way of understanding things, how a signal can basically feed from one place to another place and build up your system in a kind of a picture. So there's various rules as well for actually combining blocks together. If we represent things in terms of transfer functions, quite often we'll end up with some construction, what we've built up using all of these pictorial relationships and the signal flows. But quite often there's some simple things we can do to derive the overall transfer function just looking at the drawings, right? So imagine we had just two blocks in series, right? So we have got two transfer functions in series. Well, first of all, we can imagine a midpoint here. So we've got x of s is the input signal, goes through h1 of s, generates z of s, which is an intermediate value. This then goes through h2 of s, and we end up with y of s. It's obvious, right? So that the z of s is going to be x of s times h1 of s, right? So if we want to know what the z of s is, it's just going to be the input multiplied by the first part, which is the transfer function of the first block. And then the second part, the y of s, is going to be just z s multiplied by h2 of s. And we can substitute then the z of s into the second expression, and what we end up with is y of s equals x of s, h1 of s, h2 of s, right? So it's quite clear that we can consider going through h1 of s and h2 of s as just going through another block, which is just the product of their values. And that will generalize to multiple blocks in series. So that's a very, very trivial way of combining things in series together, just by multiplying their transfer functions. If we have two things in parallel, we have to bear in mind, we are dealing here with linear systems. So the output, therefore, is just going to be the sum of the actual parallel blocks. So the y of s here is going to be the sum of the x of s times h1 of s plus x of s times h2 of s. And if we simplify that further by taking the x of s outside, factorize it out, what we can see is we can simply replace the parallel blocks with a single block represented by the sum of their transfer functions. Again, quite simple to do. Slightly trickier and very, very important for control engineering is what is the effective transfer function for a closed loop system. And this is a typical thing that comes up a lot in control engineering. So we've got a gain of, this could be the plant, it could be the plant and also some controller. But what we've got is we've got this system here that we're going to now use feedback on. So we're going to feed back a path here through some feedback function and take it away from the input. So this is a typical negative feedback scenario. The input's going to would typically be our goal, and the output would be typically what we want the system to achieve. So how can we think about this? Well, first of all, let's think about the bit at the top as being the forward path, because the signal's going forward, and the bit at the bottom is going to be the feedback path, because the signal's coming back from the output and being taken off the input. First of all, we can immediately see if we write here a value for the value of the signal coming out of this differencer, we can say that's going to be the error signal. Let's write that as E of S. And if this is E of S here, then E of S times G of S gives us the signal here, which is going to be ES G of S. Now we want to work out what's this signal here going into the subtraction, and we can see that what was going into this feedback path is Y of S. So Y of S multiplied by H of S gives us the value going in here. So immediately now we can say, well, we know we can say what E of S is now, this bit here, because it's got to be X of S here, take away this thing here. right? So x of s, take away y of s, h of s. And we've already written, basically, that y of s, well, in fact, we haven't written it, but we can see that y of s is e of s, g of s. This here, right, is the same as the actual output of the system. So what we're going to do is we're just going to substitute this y of s term into this one here, right? Then all we have to do is just start, well, first of all, we multiply out, and we collect factors of y of s, right? So we're collecting one y of s there, and all of this lot here. So we have y of s multiplied by 1 plus h of s, g of s equals x of s, g of s. And then what we care about is the transfer function, which is the output divided by the input, so ys divided by x of s. So we just divide both sides by all of this term. And what we end up with is g of s divided by 1 plus g of s, h of s. Right? So it's a nice simple result, but very, very important. So let's think about one simple, well, here is an example which uses all of that, well, some of that, not all of it, what I've just said. We've got two things in series here. We've got something happening afterwards, we've got something happening before, and we've got a feedback loop. So how would we simplify that? Well, first of all, let's just put on that x of s is the input and y is y of s, y pf of s is going to be the output. Here's just going to be y, well, this is y pf of s because this is after the post filter. This is just the bit after the loop. And this is the feedback path here. And that's the error there. And that's the input to the plant there. We're not going to need all of these. But let's just do the thing now by simplifying it. So what we can see, first of all, we can probably see that those two things there are in series. So it's very easy to write them as a single block. Right? Two things in series can be swapped for a block where both of them are replaced by a product of their transfer functions. So we can replace that with a product of those two transfer functions. Good. That's made it. That was easy. Now we can see that we've got a block here which is corresponding to our feedback block. So all of this is the forward path, and all of this is the feedback path. So we can just use our simple relation that this basically is equivalent to forward path divided by 1 plus forward path times backward path, feedback path. So this is the G, and this is the H in this case. So this is, we put this into the G and put this in the H in that formula, and we see we get a single block, which does the equivalent transfer function to the feedback block. And the rest of it's quite simple, right? So now we've just got three things in series. So all we have to do is multiply them together, right? So we know that they're all basically in series, so we can just multiply this transfer function with this transfer function and with this transfer function, right? And then that's it, we're done. So very, very briefly to summarise just some of the simple reduction rules, the thing to always bear in mind when you're doing these things is the signal's got to be the same before and after you've done it, right? So multiplying two things together corresponds to going through this one and then going through that one, right? So this just multiplies the input by g of 1, and then you end up multiplying what comes out by g of 2. So we can just swap those for a single block. Two things that you're adding together, looks like the plus sign has disappeared, ends up just by adding the two paths, a transfer function for the paths together. And this is a good example of when we're actually moving summing points. You can move things around, but you should always bear in mind we always need the signal to be the same after you've done it as it did before. And when I say the signal, I mean the output signal in this case, right? So we want this bit coming out of the G to be the same if we just take something away in front of it or take something away after it. And what we see is this negative component, right, gets multiplied by the G. So if we move this pickup, the summing point, to after the G, what happens is, well, it's not getting scaled in the same way, so we've got to put the scaling in first. So we have to scale it so we always get the same result. Same principle when you're moving from ahead of a block. In this particular case, right, we're taking something off, right? We're taking this value off. So if we then we want to move this to in front of this G block, what happens then is what this component's going to happen to it. It's going to get scaled by G. So in order to account for the fact it's going to get scaled by it, we've got to divide by it first, and then we end up with the same thing. So here we're picking off something from behind the block and we want to put it in front of the block. So in this case, it's not getting scaled by G. So if we put the pick-off point in front of this block with the G in it, then the signal's going to have been scaled by G, and then we've got to divide by G to get it back to like it was before. Again, we're picking off something that was ahead of a block and we want to move backwards. We see that the value coming through here that we're picking off is getting scaled by G. So if we want to take it off before the G, we've got to account for the fact that we've now got to scale it as well. Otherwise we don't get the same value. And the eliminating feedback loop, we've done that one already. Again, that's one of the most useful formulas that you'll come across in control engineering probably. And the special case, of course, is when H is 1, in which case the H there turns to a 1 and we end up with an even simpler formula. What may be not completely obvious, but if you think about it again in terms of what happens at the output, because this is all a linear system, right, we're just adding stuff together, it doesn't matter which order you do it in. So if we got something taking off something from the signal and then something else taking something off from the signal, it doesn't matter if you swap the order around, because you end up with the same signal coming out, and that's the bottom line. When you're doing these things, if you want an intuitive way of understanding it, just bear in mind, what is happening to the signal. I can move things around, but after I've done it, the thing coming out's got to be the same, and that's the important point to bear in mind.